Hi guys, today we have non-exact differential equation. Okay, an equation of the form m the x plus n the y equal to 0, just as the case of exact, but in this case, non-exact equation, an equation of this form is said to be non-exact if and only if partial differentiation of m with respect to y is not equal to partial differentiation of n with respect to x. So if the partial differentiation of m with respect to y is not the same as the partial differentiation of n with respect to x, then the equation is said to be non-exact. And for us to continue the solution, we have to find the integrating factor. We have to find the integrating factor such that the equation will be what? Exact. Like, we're going to find the integrating factor now and use this integrating factor to multiply the original equation so that we can be able to what? Make the equation exact before we can be able to continue the solution. So now, method / step of finding integrating factor. So once an equation is not exact, what we do is to find the integrating factor, and of course the symbol is mu. We'll find the integrating factor and use this integrating factor to multiply the given equation in order to make it exact. So when we multiply the given equation with the integrating factor we found, and the next thing to do is to check if the equation is now exact, and eventually if the equation is exact, we can now continue the actual solution. Okay, so to find the integrating factor, the first thing we'll do is we have our step 1. We check if partial differentiation of m with respect to x minus partial differentiation of n with respect to, partial differentiation of m with respect to y minus partial differentiation of n with respect to x over n equal to f of x alone. So if the partial differentiation of n with respect to y minus the partial differentiation of n with respect to x all divided by n, if it is a function of x alone, then we can find our integrating factor. But for instance, if the partial differentiation of m with respect to y, that this particular term here, if it is not a function of x alone, then we can equally check the alternative. Also, we can also check to see if partial differentiation of n now with respect to x minus the partial differentiation of m with respect to y all over m, to check if it is a function of y alone. So if this partial differentiation, this setting here, if it didn't give us a function of x alone, then definitely this particular term here must give us a function of y. So it can be a function of x, it could be a function of y, depending on the one that gives you that comes out first. So you first of all check if this is actually a function of x. If it is a function of x, let's interpret this one first. Let's interpret the step 1. Let's consider this. Assuming we have a function of x. Assuming we have a function of x, our integrating factor mu is actually equal to exponential integral of that our f of x with respect to x. Then the f of x we got here, we put it up here, and then find the exponential integral. Whatever thing we have, we integrate f of x and then remove the exponential by applying the natural logarithm of both sides. And of course, we have our mu, this integrating factor. So this is just like a formula, but when we get into the normal solution, you see how we evaluate it. Then if the partial differentiation actually gave us a function of y, that is when we decide to do the partial differentiation of n with respect to x minus that of m with respect to y divided by m, and at the end of the day we have a function of y alone, then our integrating factor, assuming f of y as our answer, assuming this particular term as our answer, mu will be equal to integral of exponential of integral f of y with respect to y. So depending on the case, as the case may be, the differential value subtracted divided by n could be a function of x, it could also be a function of y. So when it is a function of x, then you got a function of x alone, the integrating factor is equal to exponential integral of f of x dx. Then if it is a function of y alone, the integrating factor is exponential of integral of f of y dy. Alright, so this is the basic. Let's get into a particular solution for you to appreciate and understand how this situation works. And don't forget, when we get the integrating factor, we're going to use it to multiply the given equation in order to make it exact before we continue the solution. Thank you, and let's get to the example.